We are resuming the workshop after this longer break than that plan. So Quentin Villemar from LETI will continue the presentation on the silicon photonic platforms at LETI.
Thank you. Good morning, everyone. So I'm going to present the silicon photonics platform of LETI. Okay, so this is the outline of my talk. So I will start by presenting the Silicon Photonics lab, and I will review the main applications of the lab. Then I will present briefly the fabrication platform and the device library, and I will spend time focusing on some building blocks which are very important for photonics. So very good results that we have on low propagation losses waveguides. A way to do 3D photonics to stack layers to have waveguide in silicon and in silicon nitride. I will present main active devices, modulators and photodiodes, and a way to integrate 3.5 material on silicon to make hybrid lasers. And I will finish by presenting what we do in the 300mm platform. Okay, so the Silicon Photonics lab of LETI, we have 4 types of activities, which are first design, optical simulation, but also design kits. Then, of course, fabrication, so process integration and processing of the wafers in 200mm and 300mm platform of LETI. Then we can very advanced capabilities in terms of testing with automatic prober of 200 and 300mm. So for optical test, but also electrical up to 64 GHz. And finally, packaging of circuits to make module demonstrations. So now let's review the main applications of silicon photonics. So I will start with a historical application, which is high-speed interconnects or datacom. So it's historical in the sense that silicon photonics was first developed in our lab targeting this application. And it's now quite mature as some companies are already selling products based on silicon photonics for datacom. But still, it's very important applications for us, and we still work a lot on this type of circuits. And it's a good way to understand the main building blocks of this application because they are used in other applications too. So I will describe a little bit the different circuits that we have in datacom. So transmitter and receiver circuits. So in the transmitter circuits, for example, you have first a laser source, several lasers if you want several wavelengths. Then you need a modulator, electro-optical modulator to convert the electrical data to optical data. And then you want to combine the different wavelengths, which are different channels, using a multiplexer. So then the light is in a single waveguide, and you want to extract light from the chip to an optical fiber, and then you use a coupler, for example, a grating coupler. So then the light is traveling inside the data center in an optical fiber, and it's going into another circuit, which is called the receiver. So still you need a coupler, a grating coupler to get back into the chip, a demultiplexer this time, and a photodiode to detect the signal and to convert it back to electrical. Okay, so this is a very important applications, but we have some other applications that we target now. So the next one that is an emerging application, but we have many projects going on this application is LiDAR. So using photonic circuits to make optical phase array to scan an area, for example, in automotive applications. And it's a way to scan the area with lights without any mechanical parts. So it's much more compact than a mechanical LiDAR, for example. And so we have many projects in progress concerning this application. Another emerging application is neuromorphic computing. So it's using photonics circuits to do calculations which are useful for artificial intelligence. So we are a little bit less advanced on these applications, so I go faster. But it's very interesting to make this type of circuits to have faster calculations. Another application which is emerging, but which we are very active right now is quantum photonics. So quantum computing, but also quantum computations. So in both applications, computing and communication, the type of circuits and the building blocks are similar, and it's described on this circuit here. So as we deal with quantum, we are manipulating qubits, and qubits are photons, single photons or photons pair. And first you need to generate qubits. So to that, we need a resonator and generate a ring resonator. And we have to have a good generation of qubits, we use nonlinear effects. And to have something efficient, we need very low propagation losses in the waveguide. And we have the world record, actually, in terms of propagation losses in silicon nitride ring resonators with 3 dB per meter. And we were able to demonstrate frequency comp, as shown on this spectrum here. And each line represents integral photons, symmetric with respect to the central line. So then when we have generated the qubits, we manipulate them inside the circuit, and more classical circuits made of interferometers. And at the end of the circuit, you need to detect a very few number of photons, so generally it's single photons. And for that, we need superconducting detectors, and we're working on developing superconducting detectors on silicon waveguides. Okay, so I reviewed the main application, so now I will give you some information about the fabrication platform. So this is a view of the fabrication platform. So it is a cross-section of the different layers that we use and how we integrate them together. And so this platform has been developed as part of the IRT program. So it's based on SI wafers as a starting material. And then we have a lot of patterning steps for silicon, but also for doping layers. Then we can integrate silicon nitride layers. We can integrate the heater level for phase tuning, and the back end of line with 2 levels of metals. So it's more than 200 steps, fabrication steps, 24 lithographic levels, and a lot of different devices that we can make out of this fabrication platform, with some example on the right with SCM pictures. Okay, so now I will detail some results that we have on some building blocks that are useful for the silicon photonics platform. So the first one is very basic, but it's very important too. It's a silicon waveguide. So we had a very important work as part of IRT Nanoelec in collaboration with CNRS LTM lab in order to reduce roughness of the silicon waveguides. And by reducing the roughness of the waveguides, we have dramatic reduction of propagation losses of this waveguide. And so we had very, very interesting results on a specific process, which is a smoothing annealing at high temperature and presence of H2. And the reduction in terms of propagation losses is shown on the right graph here. You see in orange without this process, propagation losses, and in blue when we apply this process, and the reduction is very, very large. And we have now the state of the art in terms of propagation losses. And so this process is now integrated in the platform, and it's offered for our partners. So it's a very important result for us. Another building block, I already spoke about that, is silicon nitride. So as part of the platform, we can integrate silicon nitride wave layer on top of silicon, and we can make waveguides in silicon nitride. And we have some advantages to use silicon nitrides in combination with silicon. So the refractive index is lower, and very important too, the thermo-optic coefficient is also lower. So for the thermo-optic coefficient, we can use it to build devices which are less sensitive to temperature. And for example, the multiplexer which is useful in transceiver circuits. I have the schematic here of the transmitter circuits for data communication applications. It's important to have this multiplexer, which is not very sensitive to temperature, because in the data center, you have a very different temperature change between the transmitter circuit and the receiver circuit. So we've demonstrated multiplexers with low thermal sensitivity. Silicon nitride is also interesting for a coupling scheme, so to couple the light from the chip to the optical fiber. And we've demonstrated broadband grating couplers in silicon nitride and broadband edge coupler in silicon nitride too. Okay, so now I will say a few words about active devices, which are very important for the TACOM application too. So first, the PN junction modulator, which is based on Mach-Zehnder interferometer. So we have a PN junction in the middle of the waveguide, and by applying a bias, we can tune the interferences of the interferometer at very high frequency. We can go up to 25 gigahertz in terms of bandwidth, and in terms of data rates, we've demonstrated 64 gigabits per second NRZ and 32 gigabo AM4. So it's very interesting for high-speed interconnects. So associated with the modulator, we have the photodiodes that we need to be as fast as the modulator. And the geometry we use is silicon germanium silicon with a germanium sandwiched inside the silicon. And we've demonstrated high frequency too with 35 gigahertz bandwidth and 64 gigabits per second NRZ transmission. Okay, and the last important building block is about 3.5. So we integrate 3.5 material epitaxis on silicon in order to make hybrid lasers. So how does hybrid laser works? So you have a schematic of a DFB laser on the top right of the slide. So the gain medium is in the 3.5, and the grating of the laser is in the silicon. So the cavity is in between the 3.5 and the silicon. So doing that is very interesting in terms of packaging complexity. It reduces the packaging complexity, so it's why it's very interesting. So the work we have done as part of the IRT Nanoelec program is to develop a process of the 3.5 in a 200 millimeter, the 200 millimeter fab of CLET. So we start by bonding a die of 3.5 epitaxis. You see here a picture of die bonding of 3.5 on silicon, and then we process it in 200 millimeter. You see here a SEM picture of pattern 3.5 waveguides with silicon waveguide underneath, and then we finish with the backend associated with the 3.5. And doing that, we've demonstrated a functional laser. So, for example, here you have a spectrum of a DFB laser. Okay, and I'm finishing with 300 millimeter platform. So what I've presented now in terms of results, it has been obtained in the 200 millimeter platform of CLET, but we are moving now to 300 millimeter. So everything that I've shown, we're transferring it to 300 millimeter, and we have already some very interesting results. So why 300 millimeter? It's because it's everything is better actually in 300 millimeter in terms of process uniformity and control, thicknesses of material, etching control and planarization also. And very importantly, we have access to immersion lithography with a very high resolution, and we have first results with a minimum feature dimension of 60 nanometer for trenches or lines. And we also use optical proximity correction to be able to have these very small features at the same time for the lines and the trenches. So a few examples of very good results that we had in 300 millimeter. So for example, for the grating couplers, we can have these very fine features, and we can improve the insertion loss from around 2 dB per coupler to 1.5 dB per coupler. And we're still working on this optimization to improve again losses insertion losses of this very important device. So it's an ongoing work, but we're going fast, and we plan to propose a full platform very soon in 300mm. So this is a summary of what I presented. So the main fact is a very low propagation losses in silicon and in silicon nitride waveguides for classical applications and for quantum applications. The full component library that we have, and maybe I forgot to say that we propose the access to this platform as part of multi-project wafers. The building blocks with silicon nitrides in top of silicon for 3D photonics, the lasers with using 3.5, and the work on LiDARs. So I want to thank my colleagues. So all the lab have participated to these results, and also the PhD students, and of course the cleanroom staff. And I thank you for your attention, and I'm ready to answer some questions that you have.